Hello and thanks for joining. My name is Jeroen Schotsaert and I'd like to share with you some case studies that highlight how AGC is leveraging its expertise in nanocoating technology to support the battery and hydrogen industry, specifically in the development and industrialization of next-generation batteries and electrolyzers. The core business of AGC is producing glass, and glass is increasingly becoming a high-tech material. Several functionalities can be created by putting thin film coatings on the glass surface. For example, the energy efficiency of buildings can be improved by applying silver-based layers on the glass surface. Indeed, most of you will have double glazing installed in their house, while on the inner pane of the double glazing there is a very thin silver layer that will be transmissive in the visible light and will be reflective in the infrared range of the solar spectrum. These silver-based coatings will reflect the heat back inside your house and hence contribute to the insulation of your house. This photo shows you a magnetron sputtering system that is performing the coating process. The magnetron sputtering is a vacuum process, so you can see here a large vacuum vessel, and the glass sheets are conveyed in a horizontal position through this vessel while the coating is sputtered on the glass surface in a top-down process. The coating layers that are applied are only a few hundreds of nanometers thick, and the coating is a multi-stack with different layers of metals, for example silver, and dielectric materials, for example zinc tin oxide and silicon nitride, to make an optical filter, transmitting in the visible range and reflective in the infrared. The equipment used by AGC is engineered, assembled, and installed by its engineers located in Germany. This group has over 40 years of experience with the manufacturing of glass coaters, and the sputter deposition sources are all in-house designed and manufactured by the team. The glass coatings are developed by the researchers in the R&D Center in Belgium. Now, with the creation of the new business unit AGC Plasma Technology Solutions, AGC is bringing its know-how in coating technology available to a broad range of other industries. The team is leveraging its long experience in the glass coating business to design and build low-pressure coating equipment for other industries, like the energy storage industry. There are several pilot lines available to support prototyping, and once the product is developed and the appropriate coating technology is selected, AGC Plasma can design and manufacture the coating equipment for mass production, and we will install it worldwide and support the startup of the production at the customer. First case study is using plasma enhanced chemical vapor deposition PECVD to produce 100% silicon anodes on copper foil. This is a collaboration with GDI, an American startup headquartered in Rochester, New York, with a European headquarter in Groningen, the Netherlands. GDI's 100% silicon anodes in lithium-ion cells enable a dramatic increase in volumetric and gravimetric energy. The copper foil used is a high tensile strength copper foil produced by the company Schlenk that contains a proprietary adhesion layer to improve the durability of the anode and to avoid delamination during the swelling and shrinking of the silicon during battery cycling. The silicon is applied by a PECVD process that has been developed by AGC. PECVD is a low-pressure chemical process by which thin films are grown on a substrate surface from a gaseous precursor. In the case of silicon anode manufacturing, silane gas is used as a precursor that is reacting by bringing it in a argon plasma. The plasma gas will give the necessary energy to decompose the silane and convert it into an amorphous silicon layer. The linear PECVD source is designed by AGC. The electrodes have the form of an elongated cavity with multiple gas inputs and an arrangement of gas outputs facing towards the substrate. The process gas, argon in this case, is fed into the electrode cavity and is ionized by applying an alternating current or a pulse DC power with a frequency in the range of 20 to 100 kHz. The ionized process gases will then uniformly exit into the process chamber through a series of holes. The precursor material, the silane gas, is introduced between the hollow cathode electrodes. The precursor will decompose in the plasma gas and a uniform thin film can be deposited on substrates in the process chamber. The separation of plasma generation and precursor inlet avoids the buildup of contamination on the sources and makes these devices useful for multiple days non-stop coating campaigns. AGC has integrated the PECVD Plasma Max source into a roll-to-roll pilot line and is now capable of producing complete rolls of bifacial coated silicon anodes. In addition, AGC has signed a Memorandum of Understanding with GDI and Schlenk to upscale the technology to a megawatt scale production tool to be installed in the AGC facilities in Lauenfelde, Germany. A second collaboration is in the field of lithium metal anode production, where thermal evaporation is used as an alternative to extrusion and lamination of lithium film. Lamination of thin lithium metal becomes challenging below 20 micrometers, while thin film technology allows to tune much thinner coatings, applying the strictly necessary lithium content on the copper foil in a reliable and reproducible manner. Also, the purity of the deposited lithium by evaporation is superior compared to extruded film. Lithium has a low melting temperature of 180 degrees and high deposition rates are feasible by thermal evaporation. AGC is partnering with the Belgian startup ABBY in the European funded Horizon project called Stellar, with the aim to optimize and upgrade a thermal evaporation system where also a passivation layer can be applied in one single pass through the machine. The ultimate goal would be to develop a continuous air-to-air system where the coil is unwound in atmospheric conditions, passes through an entry lock into vacuum, moves through the process zone for lithium deposition and passivation, and is then rolled up again in atmospheric conditions. To prevent degradation of the lithium-coated film after processing, the line's exit should be integrated into a dry room. The third partnership is a collaboration with the Swiss startup Battery for the deposition of a solid electrolyte and cathode material by magnetron sputtering. Magnetron sputtering is a PVD technology where the vacuum chamber is pumped to a base pressure of 10-6 millibar by a combination of a mechanical pump and turbomolecular pumps. There can also be a need for cryogenic pumps that are very effective to catch the residual water in the vacuum vessel. The target made of the desired coating material is put inside the vacuum vessel, and a gas, for example argon, is introduced to reach a working pressure of the order of magnitude of 10⁻³ millibar. A high voltage is then applied between the target, which will be negatively charged and become the cathode, and a suspended anode. A plasma is created. The positively charged gas ions are attracted towards the cathode and will strike the target material at an extremely high velocity. The bombarding ions eject atoms from the target surface, which move across the vacuum vessel and are deposited as a thin film of material. The process can be performed in an inert atmosphere, like argon to deposit metal films, or in oxygen to deposit oxides, or in nitrogen to deposit nitrides. By putting several cathodes, one next to each other, a complex coating stack can be deposited in one single pass through the machine. Battery is using magnetron sputtering to deposit a solid-state electrolyte consisting out of lithium, phosphorus, oxynitride, LiPON in short, and the cathode of the battery cell. This is challenging, particularly for the electrolyte, as good electrolytes must have high electronic insulation properties. Sputtering electrically insulating materials is, however, difficult and mostly done by reactive radio frequency sputtering, a technology that is not really suitable for mass production due to limitations in applied power, heat load, expensive electronics, and the need for RF-compatible vacuum deposition chambers. Most large sputter deposition tools used for mass production, for example for applying low emissivity coatings on glass sheets, are not RF compatible and use DC, pulse DC or AC power supplies for the application of the dielectrics and metal layers. AGC is supporting batteries process development by using doped LiPON targets where a conductive additive enables DC sputtering and where that dopant is removed during reactive sputtering to achieve an electrically insulating final layer. This is a fourth and final example. I will explain the sputtering of a protective anti-corrosion layer on the porous transport layer for a proton exchange membrane electrolyzer. The porous transport layer, or PTL, plays a critical role in facilitating the electrochemical reaction that splits water into hydrogen and oxygen. The PTL is located between the catalyst layer and the bipolar plate. Considering the acidic environment at the anode side of the PEM electrolyzer, the titanium needs to be protected with a thin anti-corrosion layer, and platinum is widely used. AGC implemented a plasma etching process for the PTL, followed by a sputtered undercoat and a platinum layer applied by HiPIMS power supply. The use of HiPIMS power supplies for the deposition of undercoat and platinum layer allow for the deposition of dense layers with superior adhesion to the PTL. Very thin layers can be applied of only a few tenths of nanometer thickness, and so the magnetron sputtering is an attractive substitute to electrochemical deposition for cost reduction reasons. As a conclusion, the thin film coating technology is a well-established technology in the glass industry, and AGC is now bringing that technology available for the next generation battery manufacturing and for hydrogen applications. First case study was for the use of the PECVD source to convert silane gas into amorphous silicon to produce 100% silicon anode. The second example was the thermal evaporation of lithium for lithium metal anode production as an alternative for lithium foil lamination. The third example was about the sputtering of solid electrolyte, particularly challenging because an electrolyte is an insulating material. And a fourth and last example was dealing with the sputtering of a platinum protective anti-corrosion layer on the PTL for a PEM electrolyzer. In case you have interest to discuss your application with AGC Plasma Technology Solutions, don't hesitate to reach out to Cameron or myself, and we will be glad to help you. With this, I come to an end of this presentation. Thank you for listening. Bye-bye.